Good afternoon. This is Jeff Patella, and I'm here with Zach Boyette and Prince Singh, and welcome to our presentation on the evolution of deep learning architectures. Today, we'll guide you through how convolutional neural networks, or CNNs, have evolved over the past decade and their impact on real-world applications. We'll focus on 5 key architectures: AlexNet, VGG, ResNet, Transformer, and EnergyNet, exploring their design principles and advancements.
Deep learning has transformed artificial intelligence, enabling it to tackle complex problems in fields ranging from structural biology to medical imaging. CNNs have played a pivotal role in this evolution, starting with AlexNet's breakthrough in 2012. In this presentation, we will analyze the progression of CNN architectures, their computational efficiency, and their real-world applicability using the CIFAR-10 dataset, which has a benchmark for evaluating machine learning models due to its standardized nature and manageable size.
The roots of CNNs date back to Hubel and Wiesel's research on the cat's visual cortex in 1959. Their findings inspired the neocognitron in 1980 and eventually LayNet 5 in 1998, which demonstrated CNN's potential for image processing. However, it was AlexNet's success in the ImageNet competition in 2012 that ushered in the modern era of deep learning. Since then, architectures have evolved to address challenges such as the vanishing gradient problem, computational efficiency, and scalability, incorporating features like batch normalization, skip connections, and attention mechanisms.
The impact of CNNs extends far beyond computer vision. In structural biology, models like AlphaFold predict protein structures with unprecedented accuracy, accelerating drug discovery. In genomics, CNNs analyze DNA sequences to identify genetic disorders. Medical imaging has been revolutionized with automated systems detecting tumors and retinal diseases. Additionally, CNNs contribute to environmental monitoring by analyzing satellite imagery for climate science and oceanography. These applications demonstrate CNN's versatility in solving diverse global challenges.
Our methodology involved implementing and testing 5 key CNN architectures: AlexNet, VGG, ResNet, Transformer, and EnergyNet, using the CIFAR-10 dataset. This dataset consists of 60,032 x 32 color images across 10 classes. All models were trained using TensorFlow or Keras in a GPU-accelerated environments to ensure consistency and practicality. Key techniques include early stopping to prevent overfitting and learning rate scheduling to optimize training and uniform processing across all models. By standardizing our experimental framework, we ensured a fair comparison of each architecture's performance, accuracy, and computational efficiency.
AlexNet marked the beginning of the deep learning revolution in computer vision, achieving groundbreaking performance in the 2012 ImageNet Large-Scale Visual Recognition Challenge. This architecture introduced several key innovations, including the use of ReLU activations for faster training, dropout layers to reduce overfitting, and overlapping max pooling to enhance feature extraction. AlexNet's large kernel sizes, specifically 11 by 11 and 5 by 5 convolutions, effectively captured broad spatial patterns in input images, making it a significant improvement over traditional machine learning methods. However, this design was not without limitations. With 60 million parameters, AlexNet was computationally intensive and required 2 GPUs for training, a major constraint at the time. Despite these challenges, AlexNet's success demonstrated the potential of deep learning in computer vision and set the stage for further innovations. It served as a foundational model, inspiring architectures that sought to improve accuracy and efficiency.
The VGG architecture took the ideas introduced by AlexNet and refined them into a more systematical or methodical approach. One of its most notable contributions was using smaller 3x3 convolutional kernels throughout the network. By stacking these smaller kernels, VGG achieved some of the same effective receptive field as larger kernels, but with fewer parameters and more nonlinear layers. This change allowed for deeper architecture while maintaining computational feasibility. The systematic channel doubling in VGG networks ensured a clear progression of feature complexity, with early layers capturing the basic images and textures, and deeper layers identifying more abstract patterns like objects and faces. VGG demonstrated that increasing network depth could significantly improve performance, and it could achieve higher accuracy on datasets like ImageNet. However, this came at the cost of substantial increase in computational requirements, with some versions of VGG having over 130 million parameters. Despite this, its modular and regular design has made it a benchmark in deep learning, influencing many subsequent architectures.
ResNet, or residual network, revolutionized deep learning by addressing one of the most persistent challenges in training deep networks: the vanishing gradient problem. Traditional architecture struggled as it became deeper with gradients diminishing as it propagated backwards, making it difficult to update weights effectively. ResNet introduced the concept of skip connection, which allowed gradients to bypass multiple layers, ensuring effective training, even for networks with hundreds or thousands of layers. This innovation enabled ResNet to achieve exceptional performance while maintaining manageable training times. ResNet's residual blocks encouraged feature reuse and enabled the network to learn residual functions instead of direct mappings, which proved to be a more efficient way of training. Beyond its technical contribution, ResNet has a profound impact on the applications of image processing, object detection, and medical imaging. Its scalable design has influenced the development of numerous advanced architectures, making it a cornerstone in the evolution of deep learning.
Transformers introduced attention mechanisms to convolutional neural networks, fundamentally changing how networks process spatial relationships and images. Unlike traditional CNNs that rely solely on local feature extraction through convolutional layers, transformers incorporated self-attention mechanisms that dynamically focus on relevant features across an entire image. This shift allowed for a more holistic understanding of spatial relationships, enabling networks to capture long-range dependencies between features. Originally developed for natural language processing, transformers demonstrated their versatility by achieving state-of-the-art performance in computer vision tasks. They also introduced a new paradigm of parallel data processing, significantly improving computational efficiency compared to the sequential processing in traditional CNNs. The success of transformer-based architectures highlights the growing trend of integrating ideas from multiple domains, showcasing their adaptability for tasks like object detection, segmentation, and even structural biology. This breakthrough underscored the potential for hybrid architectures that combine the best aspects of both convolution and attention mechanisms.
EnergyNet represents the culmination of nearly a decade of architectural innovations, combining elements from earlier models while introducing its unique features. One of EnergyNet's key strengths is its efficient block design, which uses parallel pathways to process diverse feature streams simultaneously. This enables the architecture to capture fine-grained details while maintaining computational efficiency. Additionally, EnergyNet employs advanced skip connections inspired by ResNet, but with a more sophisticated pattern of information flow that minimizes redundancy and maximizes feature reuse. Channel reduction techniques, another hallmark of EnergyNet, ensure the model maintains high performance with fewer parameters, making it ideal for deployment in resource-constrained environments. EnergyNet's adaptability and scalability have made it a go-to choice for applications requiring a balance of accuracy and efficiency, such as real-time image analysis and edge computing. By synthesizing innovations from the past decade, EnergyNet exemplifies the progress made in CNN design and sets a high bar for future architectures.
In this study, we implemented 5 representative CNN architectures: AlexNet, VGG, ResNet, Transformers, and EnergyNet. Each model was trained and evaluated on the CIFAR-10 dataset, a standardized benchmark consisting of 60,000 images across 10 classes. We used a consistent pre-processing pipeline for all models, ensuring a fair comparison. Data augmentation techniques such as horizontal flipping and normalization were applied to enhance the diversity of the training set. The models were trained using TensorFlow or Keras in a GPU-accelerated environment to leverage high-performance computing resources, specifically Colab Pro with 15 gigs of GPU RAM. To evaluate the models, we implemented early stopping to prevent overfitting and used the Atom Optimizer to ensure robust convergence. The performance metrics considered include test accuracy, training times, and parameter count, offering a comprehensive view of each of the architecture's strengths and trade-offs. This experimental setup allows us to analyze not only how these models perform, but also their computational efficiency, scalability, while shedding light on their practical applicability in the various domains.
The comparative analysis reveals trends in how different CNN architectures learn. AlexNet, despite its relatively modest 17.30 million parameters, reaches almost perfect accuracy in only 10 epochs, showing the effectiveness of its pioneering design. VGG, with its substantially larger architecture of 134.90 million parameters, shows similar convergence behavior, achieving almost perfect accuracy in only 9 epochs. ResNet demonstrates particularly efficient learning. While utilizing 105.34 million parameters, it approaches nearly perfect accuracy, slightly faster than its predecessors. The Transformer architecture achieves comparable performance with a significantly reduced parameter count of 53.58 million, reaching almost perfect accuracy in only 8 epochs. Finally, EnergyNet, representing the most recent development with 51.95 million parameters, shows similar learning dynamics, achieving 90% accuracy after about 15 training epochs. The reason EnergyNet did not converge like the others may be because the depth of the CIFAR-10 dataset is only 3. IFAR-10 images are RGB, 3-channel images, so their depth/number of channels is 3. Each image in the CIFAR-10 dataset is a 32 by 32 by 3 color image, where the width and height are 32 pixels, and the depth is 3, red, green, blue. All architectures demonstrate consistent learning patterns despite their vastly different parameter counts. This suggests that their architectural innovations have focused on efficiency rather than raw performance gains in reaching this accuracy threshold.
This slide visually compares the results across the 5 models tested. On the left, we have a bar chart summarizing the size of the neural network for each architecture, ranging between 17 million and 135 million parameters. On the right, you can see the training curves for each architecture, showing how they converge at different rates and exhibit different learning characteristics.
This comprehensive analysis of CNN architectural evolutions from 2012 to 2021 highlights a remarkable progression in deep learning design. AlexNet laid the foundation with its innovative use of convolutions and max pooling, establishing the feasibility of deep learning for computer vision tasks. VGG took this a step further, showing how increasing depth and using small convolution kernels could improve feature extraction and overall performance. ResNet introduced skip connections, a game-changing innovation that addressed the vanishing gradient problem and made training deep network possible. This approach not only enhanced accuracy but also demonstrated the importance of residual learning in optimizing network performance. Transformers revolutionized CNN design by integrating the attention mechanism, enabling dynamic feature focus and improving the efficiency of spatial relationship processing. Finally, EnergyNet showcased how modern architectures balance computational efficiency with strong performance, setting a new benchmark for resource-constrained environments.
Our findings demonstrate clear trends in CNN development. Newer architectures are achieving higher accuracy and becoming increasingly efficient. This balance of performance and computational cost is critical as AI applications expand to edge computing, mobile devices, and real-time systems. The experimental results underscore the importance of considering parameter count and accuracy when designing CNNs for practical deployment. Looking ahead, we anticipate further integrating attention mechanisms and hybrid models that combine the strengths of CNNs and transformers. Additionally, the success of architectures like EnergyNet suggests that future research will continue focusing on parameter efficiency and scalability. These insights are invaluable for researchers and practitioners aiming to harness the power of CNNs across diverse domains, from healthcare to environmental monitoring. This project provides a roadmap for understanding the innovations that have shaped CNN's evolution and offers guidance for future deep learning advancements. We would like to take a moment to express our gratitude. First and foremost, we thank Dr. Hao Long Zwang for his invaluable guidance and mentorship throughout this project. His expertise provided the foundation we needed to conduct our research and achieve meaningful results. We also thank Arizona State University for creating a collaborative environment and providing the resources necessary for this project. Access to high-performance computing systems, libraries, and workspaces has played a critical role in enabling us to implement and evaluate advanced deep learning models. Finally, we acknowledge the support and effort of each team member. This project would not have been possible without the dedication, hard work, and collaboration of everyone involved. Thank you for being part of this incredible journey of exploring the evolution of convolutional neural networks.